Hello everyone. Today I'll talk about differentially oblivious Turing machines. My name is Ilan Komargodski and this is based on joint work with Elaine. Consider the following simple motivating scenario. There is a weak computational device, think of a laptop or some small personal computer, that wishes to store and access a large database. Unfortunately, the device is too small and doesn't have enough storage, so it cannot store the whole database locally. So a natural approach would be to send the database to some remote server, think of the cloud for that matter, and ask the cloud to store the database. While this completely solves the storage problem, it introduces a privacy problem. Now the server can just see the database and all privacy for the client is lost. A natural solution would be for the client to first encrypt the database before sending it to the server, store the key locally, and only then send it to the server. At this point, it's clear that the privacy problem we had is solved, right? The server cannot access any of the data inside the database because it's encrypted. However, problems start when the client starts to access the data. It is well known that the mere access patterns, if done naively, might leak a lot of sensitive information about the underlying database. So to this end, Goldrake and Ostrovsky introduced in the late 80s and early 90s the notion of Oblivious Ram. An Oblivious Ram, or ORAM for short, is just an algorithmic approach that provably obfuscates the access patterns, the observed access patterns. In slightly more detail, what it does, an Oblivious Ram, it does something analogous to an encryption of the access pattern itself, so that the observed access pattern is somewhat independent of the underlying data. And the exact mathematical formalization of this independence property could be any of computational, statistical, or perfect, depending on the application in hand. And all of the ORAM constructions that are currently known work by permuting the data in memory and continuously shuffling it upon every access. So in terms of constructions, we have pretty great constructions. We can obliviously simulate any RAM program, any RAM machine where the RAM is of size capital N, using only logarithmic overhead or log squared overhead, depending on the type of security that we aim for. Namely, if we settle for computational security, then using one-way function, there is a compiler that takes any RAM machine and translates it to another RAM machine that implements the same functionality, but where every access is translated into logarithmically many accesses, and the security is computational. So this is great. If we want statistical security, we can do the same, albeit with log squared overhead. So this is great, and this is also great because there is a matching lower bound. Namely, we know that every ORM compiler must suffer from logarithmic overhead. So namely, whatever compiler you come up with, whatever compiler you come up with, the simulated RAM machine will make logarithmically more accesses per access on average than the insecure version. So this was proven, a version of this was proven by Goldrake and Ostrovsky back in their original work, and there was a refinement by Larsen and Nielsen a couple of years ago. And even more interestingly, Jacob, Larsen, and Nielsen showed last year that even very simple and specific algorithms or data structures already require logarithmic overhead. So you don't even need to consider general RAM computation. You can just consider very simple functionalities. So in terms of upper and lower bounds, we have almost tight in some senses, or almost tight constructions. However, the lower bound also tells us very bad news. It tells us that we need to pad all of the executions of the insecure machine to the running time of the worst case input, because if we want to make sure that all of the inputs look the same in terms of the access pattern, they need in particular to run for the same amount of time. So while it seems like the overhead of an oblivious RAM is logarithmic for specific inputs, it's actually, it might actually even be linear, which is very expensive. So this is the state of the art of ORAM. Differential obliviousness is a notion that was defined a couple of years ago by Chen et al. And it's a meaningful notion of privacy, which is a relaxation of the notion of full obliviousness, which is inspired by differential privacy. So that's good. It's some meaningful notion of privacy. It tells you something about what kind of security you're going to get if you use that. However, somewhat surprisingly, we know that general RAM computations, even if we settle for differential privacy or differential obliviousness, then still we need to pay logarithmic overhead, which is this is kind of this was kind of surprising. But then it was shown by Chen et al. That specific tasks, if one considers only specific functionalities that we only knew how to get with logarithmic overhead with full obliviousness, now when we settle for differential obliviousness, we have algorithms that achieve them with only doubly logarithmic overhead. And while this may seem like only an improvement from log overhead to double logarithmic overhead, it's actually better than that because this is an overhead which is per input versus the logarithmic overhead which we have in full obliviousness, which is logarithmic of the worst case. So this is what we know about differential obliviousness. Let me just try to define what differential obliviousness gives us, or what it guarantees. So let's consider in slightly more detail the setting of oblivious simulation. So in oblivious simulation, there is a CPU, which is the green box in the middle. It's a randomized CPU. It has an input, and we think of the input as a sequence of logical operations, logical accesses to the RAM. Logical access could be go to location 5 and read the content, or go to location 10 and write some content. So these are logical accesses. And every logical access is translated into a collection of physical accesses or a sequence of physical accesses. And the physical accesses are done through the physical RAM. And the adversary is observing those. Okay, so this is the setting of oblivious RAM, of ORAM. And in oblivious RAM, in full obliviousness, what we want is that the observed sequence of physical accesses tells you nothing, tells the adversary nothing about the logical access sequence. When we talk about differential obliviousness, we consider neighboring sequences of inputs, which in our case is just neighboring sequences of logical accesses. So think about, given the left sequence of accesses, take an arbitrary axis on the left and do something else at that point. This is the neighboring sequence. Okay, so you access the same locations as on the left, except one time that you access some other location, some other new location. And now we consider the two executions, one of the left input and one of the right input. And what we want is that these two inputs will be indistinguishable for an attacker. So an attacker sees either a sequence that was generated, a sequence of physical memory accesses that was generated from the left input, or a sequence of physical accesses that was generated from the right input sequence, and it needs to distinguish which one it obtained. And differential obliviousness means that it cannot distinguish. And more precisely, what we want is that is a definition of the sort of differential privacy where we consider any possible sequence of physical memory accesses, and we say that the probability that the left input sequence caused this sequence, this physical sequence, is roughly the same as the probability that the right input sequence caused this physical access sequence, except that the difference between these two probabilities is there's a multiplicative factor of the order of e to the epsilon and an additive term, which is delta. So it's really analogous to the notion of epsilon delta differential privacy. So this is the formal notion. And this is what we know about it in slightly more detail. So I'm going to consider epsilon, which is a constant, and I'm going to assume that our goal is to obtain delta, which is a negligible function. So I will not explicitly mention epsilon and delta. The work of Chen et al. Considered a problem called stable compaction. So stable compaction is a special case of sorting, except that each element that you want to sort is associated with a very short key. The key is just 1 bit. And the goal is to put in the beginning of the array all of the elements that have the key 0, and in the end of the array all of the elements that have the key 1. And we also want to preserve the internal ordering between same key elements. So this is the problem called stable compaction. And this is what we know about it. So if we want to get full obliviousness for this problem, so this is just a special case of sorting, the best we know is to run a full oblivious sort. And this gives us n log n overhead, where n here stands for the length of the input array. We also have a conditional lower bound, which says that this is necessary. I'm going to talk about the lower bound in a second. And the result of Chen et al. Was that if you consider differential obliviousness, then you can actually obtain a stable compaction with much better overhead, namely only doubly logarithmic overhead. And they also show that this seems to be necessary. So about the lower bounds, so both lower bounds here are proven in something called the Bose-Binz model. The Bose-Binz model is a restricted model of computation for ORAM, which ties the hands of the ORAM itself, of the construction itself, in the following way. It has to treat elements as balls, as opaque balls. It cannot look at the content of elements. It can only look at their metadata. Namely, it can only look at the associated key of a ball, but it cannot do any sort of non-trivial encoding of an element. So it can only move balls around, elements around. So this restricts the model, and it gives a weaker lower bound, therefore gives a weaker lower bound. But it's still a meaningful lower bound in some natural model of computation. So this is the state of the art of what we knew about differential obliviousness. What we show is a significant generalization of this result in the following sense. We show that any computation that you can run using a Turing machine with n steps, you can actually do differential obliviously. So let me just parse out the statement. There is a very classical result from the late 80s of Pippenger and Fisher that shows that any Turing machine computation can be translated into an oblivious version thereof using only logarithmic overhead. So given a Turing machine, there is another Turing machine that has a completely fixed sequence of transitions. So it's even deterministically oblivious, and it can simulate the original machine. And it does so using only logarithmically many more steps. So the upper bound for obliviousness is logarithmic in n. We show that if we only care about differential obliviousness, so we only want to hide one transition in our execution, then we can do it in doubly logarithmic overhead. And by the same lower bound as in Chen et al.'s work, we trivially get a lower bound for simulating general Turing machines. And by using previous work that I mentioned, this Jacob, Larsen, and Nielsen work, we also have a logarithmic lower bound for full obliviousness. And the lower bound actually holds for very specific access structures or very specific data structures, like I mentioned. So specifically, it's going to be a stack or a queue. And a significant bulk of our work is to implement our differentially oblivious Turing machine in a Turing machine, as a Turing machine. And we do a lot of technical work is devoted to preserving the number of tapes and other complexity measures of the original Turing machine. So this is our main result. One corollary of our result is that for the first time, we show that unconditionally, differential obliviousness is easier to obtain than obliviousness. So here we present a specific data structure. It's a stack for that matter, stack or key or anything else. That we know that if you want to obtain full obliviousness, you need to work at least logarithmic overhead. You need to have at least logarithmic overhead. But if you want differential obliviousness, you can do it in double logarithmic overhead. And all of the previous separations of this form were conditional. So they were in the Boys and Beans model or assuming something else about the ORM. So this result is completely unconditional. Okay. So these are our results. So I'm going to tell you about how it works, how the construction works, how the upper bound works. And I'm going to focus on a specific data structure. It's going to be a stack just for ease of notation, but the same idea can be generalized to any Turing machine. And so we all know what a stack is, right? You can push an element, you can push other elements and push another element, you can pop, push, pop, push, pop, push. And the thing you want to hide is the location of your head of the stack, which just symbolizes how many elements you have. So it's trivial to see that if you don't care about security, you can just do it with linear number of head movements. So you can support n operations with only n head movements. And by the compiler of Pippinger and Fisher, if you want full obliviousness, you can do it with n times log n head movements. And you can even do it on a Turing machine. So you don't need a RAM for that. And the lower bound that I mentioned of Jacob, Larson, and Nielsen gives us a lower bound saying that logarithmic overhead is necessary even if you allow it, even if you run a Turing machine. So maybe I will just note here that what we need the stack to be in an online fashion, namely that the elements should come online for this lower bound to hold. Okay, so this is the stack. And when I say that I want to implement the differentially oblivious stack, what I really want is to hide which input sequence I'm using, the left or the right, as long as only one operation is different. So in two sequences I have here on the slide, they are completely the same, except the fifth element on the left is a push, and the fifth operation on the right is a pop. So the input sequences are neighboring according to our definition. So we want to hide which input sequence we're using. So we're going to use two tools. The first one is just an oblivious Turing machine. So we can use the Pippinger and Fisher, but we need an oblivious Turing machine with a little bit of modifications. So we actually need to modify a little bit the construction of Pippinger and Fisher. It will not be super important for this talk, but if you're interested, you can look at the paper. We also have a cleaner representation, or in my opinion, a cleaner representation of Pippinger and Fisher. So this is the one tool that we're going to need. And the second tool is a new algorithm that can estimate the number of items in a stack while maintaining differential privacy. Okay, so this is what I'm going to talk about in the rest of the talk. So we're going to estimate the size of a stack differentially private. So we're just going to imagine a pop operation as a -1 and a push operation as a +1. So our goal is to just count those numbers. And so namely the number of items in the stack is just the prefix sum of the numbers until that time. Okay, so if we push 10 times and pop once, the number of items is 9. And at that point, at the 10th time point, the prefix sum is 9. Okay. And so we can almost use as a black box an algorithm which was designed by Chen, Shi, and Song and worked it out about 10 years ago. It's an algorithm that gets as input a stream of numbers, and it gives you the prefix sum of the stream at any point in time while maintaining differential privacy. The algorithm works in some fashion, which is like a tree, where you put on the leaves of the tree, you put your numbers. So if you have a +1, you put a +1. If you have a -1, you have a -1. And every internal node gives you an estimate of some range. And the very cool trick that they have is that every leaf, because of the tree structure, every leaf only appears in the subtree of only logarithmically many nodes. So because we're using differential privacy, for every time that the leaf will appear in some node, we'll lose something in our differential private estimate. And because of the tree structure, we're only going to lose like a logarithmic factor per node instead of losing something which is linear in the number of elements so far. And it's not hard to see that their algorithm is just running their algorithm is oblivious. It's not sensitive to the value of the number. It's just doing some arithmetic computation. And it also supports elements coming online. And so one problem of using that algorithm trivially is that whenever we want to get an estimate, but just running their algorithm, whenever we want to get an estimate of the prefix sum, it costs us some non-trivial factor, because you need to compute like a summation of log many counters. And this is bad for us. So what we're going to do is we're going to truncate the tree, and we're not going to get an estimate every time step, but we're only going to ask for an estimate of the prefix sum whenever we need one, which is going to be every polylog many steps of computation. So this is like a simple amortization trick. And here's how the algorithm works. So think of the input as a sequence of plus and minus ones, and think of that we're at some point in the timeline, which is this arrow. So we have two variables at this point. We have the estimated stack size, which we denote by S bar, and we have the real stack size at this point. The real one should be hidden, and we're only going to leak the estimated one. Because we're using their differential private prefix sum algorithm, we know that the result is going to be pretty close to the estimated stack location is going to be pretty close to the real stack location. Specifically, it's something like polylog. So we will not be completely wrong with our estimate. But on the other hand, this estimate will not tell the attacker too much about the real locations. So it will not be able to distinguish whether we are in a sequence where whether we're in the input that you see on the screen, or one where one location was flipped. So that's why it's okay to leak this S tilde. And now what we're going to do, we're going to copy an area around the estimated stack size. We're going to copy it to the side. So let's say we're going to copy a location which is twice bigger than the error to the side. And the next log squared operations, we're going to do inside that oblivious step. We're going to do inside a completely oblivious stack. So we can use the oblivious Turing machine of Pippinger and Fisher to implement the next log squared operations. We're going to finish the next log squared operations. We didn't click anything during those log squared operations because we used a perfectly oblivious construction. And we're going to estimate again. At this point, we can estimate again the stack location and repeat the process. So if we just do a back of the envelope calculation, because copying a large area will cost us O(1) per operation, because we're copying once and we're going to do inside log squared operation, so it's going to cost us something like constant per operation inside that construction. The next bullet is the expensive one. We implement the next log squared operations inside in the perfect Turing machine, or a perfect oblivious Turing machine. And the overhead of that one is logarithmic in the input size, or in the logarithmic in the length of the number of length of the sequence. And that one is log squared, so the overhead is going to be actually log log of log log. Copying back is again of one amortized, and estimating again due to our trick of getting an estimate once every polylog steps, it's going to cost us again O(1) per operation by just setting the parameters carefully. So overall, the overhead is indeed going to be something like n times W logarithmic in n. This is in very high level how the algorithm works. There's a lot of details of how to handle multi-tape Turing machines and without increasing the number of tapes, but that's a little bit out of scope for this time. So let me just summarize. There are the bottom line of this work is that there are many natural problems for which obtaining differential obliviousness is much easier than obliviousness. Turing machines can be generically made differentially oblivious with just doubly logarithmic overhead, which is something that we know is false for RAM machines. And it leaves or opens lots of interesting questions, in my opinion. One is first our lower bound for our doubly logarithmic lower bound on differentially oblivious Turing machines is in the Bose-Bins model, and we don't know how to prove it unconditionally. So that's one interesting technical question. And another one is more vague, but it's just to come up with other interesting relaxations of obliviousness and to see how they relate to full obliviousness or just differential obliviousness. And that's it. Thank you so much.